Hello fellow problem solvers. So today we're going to be doing a problem from the 2012 IMO, problem number 5. I suggest you try this lovely geometry problem out for a minimum of half an hour, ideally an hour and a half to 2.5 hours, not more than 4 hours. You wouldn't have more than 4 hours on this problem in all likelihood. So without further ado, if you want to go along with us, try this out, draw the diagram, put your first ideas out on paper for the next 15 minutes. And now, without further ado, let's begin. So what do we need to do? We need to actually first draw the diagram. Okay, ABC is a triangle, BCA is 90. Bam, 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 done. Why is the first, the first diagram very lousy? Because I don't know what the problem looks like. So I first draw a lousy diagram and then I, fix it later on. So now X is a point in the interior of the segment CD. D is the foot of the perpendicular. Okay, bam, X. So K is on the point, is a point on the segment AX with BK is BC. So AX and now, whoa, BK is BC. So this is like, I do a little bit of a walk. And that's K. BK is BC. That's horrible. And L is defined symmetrically, so I'll have AL is AC. M is the intersection of these two. I need to prove that ML and MK are equal. I said I will draw another diagram, but first let's see, what is this? How are these points? This is a very weird definition of a point, right? I mean, it is to me at least. So first, let's see what's happening here. What is this AL? So what do we have maybe from first for D? Like going at the problem forwards. We know that we have dA times dB is dC squared from similar triangles. Ooh, we have AC squared is equal to AD times AB. And then this is also equal to, AL squared. And this is something that can sometimes get used in problems. You have this squared is equal to something, this other thing, because this is true because these things are, like AC is tangent to the circumcircle around this, so AL is also a tangent to this circumcircle. And in other words, we have this angle here is equal to this angle here. Could be useful, maybe not. But we also have similarly like that, we have this angle here. We have BK squared is BD times BA. BK squared is equal to BC squared is BD times BA. So we also have that, and that is going to give us that. This angle here and this angle here are identical. So these two angles sum up to be 180 minus this one. And this angle plus this one is 180 minus this one. Could that be used in any way, shape, or form? We don't know just yet. We know this angle is this one plus this one plus this one. So this angle plus this angle is going to be 180 plus this one. Is that useful? I have no clue. Really no clue at this point. And it's been a long time since I've done this problem. So we have that. Do we have anything for X? X is a variable point. It doesn't really do us much good. And now there are a couple of ways we can go about this problem. And I invite you here to pause for 20 minutes. I'm going to clear this thing, right, this text here, and draw a better diagram. And I'm going to invite you to try to see where do you want to take this? You have BD times BA. And still, how are we going to connect this to M? Maybe I can say before that something about M as well. MK is ML. What's there? Like, what is this? Is there anything we have about K, about L? Is there a power of point? Is there a circle? Is M the circumcenter of this KLD? No, it's definitely. It could be, maybe, when X corresponds to this, K and L correspond to that, and then M corresponds, no, so it's probably not. It's probably not. So the reason it's not a midpoint, I don't think that this is a circumcenter, is because as X moves closer to C, K and L move very, very close, and their intersection is somewhere around here, and that's much farther away from D. That's like sort of an intuition for how I'm thinking, why I'm saying it's probably not going to be the circumcenter of KDL. And that's about it that I see right now. So now, yeah, pause for 20 minutes. Like, there's two ways to go about this problem now. And we'll come back with the next step. So this is the first sort of way to go about the problem. We realize, wait a second, this AL squared is AD times AB. I can forget about C now. This uniquely defines the point L. A point on line here such that AD times AB is AL squared. Because that just uniquely defines the point here. So C is kind of old news now. Doesn't matter, right? I can define the problem as I have an obtuse angled triangle such that an L on here such that AD times AB is AL squared, K here, and then the intersection. Now, I've lost a point C, but I haven't really lost much. Really, I've simplified my problem. I can get back to C if I want it, but for me, it's like, wait, this is much, much cleaner to work with. And now, one question that you might ask yourself, AD times AB is AL squared, and after BD times AB is BK squared. One question I ask myself when I see a problem like this is, wait, does the triangle being obtuse really matter? Like, it's a feeling. It doesn't seem like it matters. It seems like it should matter even if this triangle wasn't obtuse, but rather it was acute. Like, what's so special about it being obtuse? Nothing. So that's the first sort of thinking that I have had actually when I try to solve this problem. So now it's like, how do I use these facts? How can I connect K and L somehow and this point M? Can I connect them to anything? And this is where the idea comes in. The next idea, which I invite you to pause for 5-10 minutes and try to come up with one. And the idea is this. Wait, I have a foot of perpendicular here. AD times AB. Where does that show up? Well, when I add the other feet of perpendiculars, I add them here, boom, boom. And I intersect with the orthocenter H. Call this B0, call this A0. XDH are collinear. And now I have this AD times AB is also equal to AX times AA0. And it's also equal to AB0 times, so it's AB0 times AH. And similarly for B. And now I have more things for L. I in fact have, this is a bit more interesting. Now, AX times AA0 is AL squared, which means that these two triangles, like AL is a tangent to the circumcircle around XK A0, which tells us what? Here's where I invite you to pause for another 5-10 minutes. And the answer is no, it doesn't really tell us. It tells us, this angle is equal to this angle. You don't get much from that, do you? Okay, no. Well, what about this one? We have AB0 times AH is AL squared. Now, AL is tangent to this triangle. Now, what's so special about this triangle? Well, what's special is that this is a right triangle, which means ALH is equal to 90. And mind you, this should also uniquely define the point L, because there's only one point such that the circumcircle with center on the midpoint of AH and radius, that midpoint H, it only intersects this as 2 points, but L is unique on this line. So we have this angle right here is now 90. And similarly for K, HKB0 is also 90. And not only are they 90, we need to prove now MLH is 90 and MKH are 90. And we need to prove that ML is MK. Well, what is that equivalent to? Pause for 10 minutes and try to push the problem further if you haven't paused so far. Because this is beautiful. This implies what? Well, if, mind you, then these 4 points are concyclic, MLHK, we know that because both of these are 90. But more to the point, if ML was MK, then the angles MHL would be equal, these two angles would be equal, but because we're at a 9, let me actually draw a diagram, a beautiful diagram as you can see. We'd have mind you, MH here is the diameter, and we would have MK is equal to ML. Well, this is 90, this is the diameter, that means that KH is KL. And that is also enough for us to prove. It's enough for us to prove that HL is HK, right? That is what's good enough here. This is also one of the reasons I really like this problem. Mind you, what did we have? And now here, if you didn't figure this out, pause again and try to solve it for another 20 minutes. Think, what does it mean? How do we define L? We define L as AL squared is AD times AB, and we show that it's a unique point on BX, which is also like the orthocenter of AHB, right? It's a unique point here such that this is 90. What should also somewhat symmetrically follow? Please pause if you have not. And the answer is, well, wait a second. AD times AB is equal to AL squared. Forced L to be this point. So we should have, this is thinking at it backwards. We should also have, if I just defined a point L here on BX, which is like B and the orthocenter, such that HL squared was HAO times HAB. I should also get that this is 90. Because there's like symmetry with respect to A and H if we're looking at L. That's what's freaking amazing about this problem. Why I love this problem. And I mean, this solution, this approach. And now we need to go at it forwards. Like, okay, how do we actually prove this? You've said it, it looks nice. How do we actually go about proving that thing? Well, let's see what we did here. We did this squared was this times this, so we had that, what's it called? And we found this was 90 because this times this was equal to this squared. So we used the fact that this angle was 90 and that this times this was equal to this squared. You see where I'm going with this? What is the opposite? Well, this times this should be equal to this squared, and then we can use the fact that this times this is this times this. Do we have that? Well, yes, because it's a right triangle. So HLA is a right triangle, so HB0. If you want, I can actually go ahead and prove like this triangle is similar to this triangle. Ergo, we have this thing. And now HB0 is HA. HB0 times HA is equal to HL squared by this similarity. And from here, we have that this is also equal to, mind you, HA0 times HB, which is equal to HK squared. On the other hand, on this 90-degree triangle, HKB. And so HL is equal to HK. And because these are both 90, we have that MK squared is going to equal what? It's going to be equal to MH squared minus, what is it, mk hk squared, which is equal to mh squared minus hl squared, because these two things are equal, and this is ml squared. Boom, boom, mk is ml, and we are done. Beautiful solution, beautiful problem. I love it. And now we go ahead and we'll do, like, say you didn't say like, oh, I kind of like C. I want to do something with C. You're going to do another solution which uses, again, an idea of a different sort of idea. Okay? And now we go to that solution. So, why do I have these two circles? Well, it's an interpretation of this. AL is AC. Another way of looking at it is a circle with center A intersects BX here, the segment BX. And same with this circle. Why are these circles somewhat interesting? Well, these are circles with centers A and B, and they are what? They are tangents to each other. That's what it means for this angle to be 90. There are some nice properties for sure, but now this is a way for us to look at what everything is here. So for these two circles, these are tangent to one another. And we know that its radical axis of these two circles is CD. So why do we know that? Well, because if we just reflect here, we'll get a 90-degree angle. This will be equal to this is equal to this, i.e. they are both on the circles with, this point is on both these circles. So now, X is a point of interest because the point X defines the points K and L. And it has the same power of point with respect to both circles. So let's see what that power of point is. It's an internal power of point. So if we intersect AK and BL with these other circles, again, we will have, say, call this point L1, call this point K1. And now here, I invite you to pause for another 2 to 5 minutes, push the problem further. Actually, for 10 minutes, push the problem further. And here's the big idea. The big idea is to now look at, okay, we have power of point. What does that give us? It gives us xk times xk1 is equal to xc times xc times xc, what I say, xc prime. And this is equal to xl times xl1, xl. And now, from power of point, we have an extra, what's it called? Extra 4 points, which are, they are concyclic. And so now we have L, L1. Actually, this was the bad way to write it, but say L, L1, K, K1 are concyclic. They all lie on the same circle. So now, what does MK equal ML? Well, it's sort of aiming at the fact that once I intersect this with this circle around L, K, L1, K1, that intersect them again, I'll have equality. And that's one thing. But there's another thing here. What would be nice to happen is another way of looking at it if we're looking at it backwards. So it's really hard to look at it backwards here. What would be a nice to happen is a question, but the more realistic one is, okay, I've intersected them. Let's see what else do I have. How do I use this now? How can I connect it to M? Let me use the fact that AL is equal to AK times AK1. Like, I've had this circle now, which I didn't have before. A as a power of point. I kind of dig here, right? I have AK times AK2. And what's that equal to? It's equal to the power of point of A with respect to this big circle. And that is equal to what? So we have AK1 times AK is the power of point with respect to this other circle. And we're curious what that is. But we know from this circle with center B, let's call this WB, WA, this big one is W. We know from WB that AK times AK1 is equal to AC squared. And AC squared is equal to what? It's equal to AL squared. Now, what does that tell us? I think you can finish it up if you take 10 minutes and try to finish up the problem from here. And the thing is, you have AL squared is AK times AK1. So AL is actually a tangent to the circle around KLL1. But that's a circle around, KLK1. But that's a circle around all of these points. So AL is actually a tangent to this circle called W. Similarly, BK is also a tangent. And then what is M? That's amazing. Then M is the intersection of these two tangents. Of the tangent from K to the circle and the tangent from L to the circle. Which means what? The power of point of M is MK squared is equal to ML squared. In other words, MK is ML. God, this is good. This is a pretty beautiful geometry problem, if you ask me, in my humble opinion. It's so nice. Just look at it. Just like that. Boom. This is a much more, it's a big bit of a perspective shift, and then, okay, how do I use the fact that this is 90? How do I take advantage of, okay, I have X is on the radical axis. How can I take advantage of that fact? Well, let me see what its power of point gives me. And I think, usually when you have a point on the radical axis and you have, like generally just two chords like this, in any sort of situation, you'll have that these four are going to be concyclic, no matter what they are. Like, right, I can have a chord here, and it's going to have, if the chord is Z, Z1, then Z, Z1, L, L1 will be on the same circle. Just through power of point. That's why this is very powerful. It's power of point. So you get there, and really once you intersect, once you get K1 and L1, it's pretty much over. You only need to realize, wait a second, okay, let me get back to AL. Again, I have AK, and then it's done. Then it's just problem over. So this is why I really, really like this problem. It has these two solutions. They're different, and they're both beautiful in their own way. Just like you. And as always, thanks for problem solving.